Hi everyone, and thank you for joining us today. My name is Layla Haslinger, and I'm the Training and Events Coordinator here at Eco Canada. Welcome to A House Doesn't Need to Breathe, But People Do, a new webinar. Do you mind changing the slide?
Oh yes, that's me.
Thank you. Before we start, we would like to take a moment to recognize the traditional Indigenous lands where Eco Canada's office is based in Calgary. At Eco Canada, we're committed to working towards a respectful acknowledgement, collaboration, and reconciliation with Indigenous peoples across Canada. This starts with acknowledging our honor and privilege to live and work within the Treaty 7 territory. Today, we are presenting from the City of Calgary, home to the Métis Nation of Alberta, Districts 5 and 6. We would also like to take this time to acknowledge the traditional territories and oral practices of the Nikiski, home of the Blackfoot Confederacy, which includes the Siksika, the Kainai, the Kainai First Nations, as well as the Tsuut'ina Nation and Goodstoney, which include the Chiniki, Bearspaw, and Wesley First Nations. Next slide, please. I also want to go over a few housekeeping guidelines for today's sessions to ensure that everyone can enjoy and participate in our session effectively. All participants are muted, so please check your audio settings to ensure that you can hear us properly. If you are experiencing any technical issues, please use the chat function on the left-hand side of your screen, and we will do our best to resolve it for you. Today's webinar is being recorded and will be available for your viewing in 24 hours. Any questions that you have about the presentation today or today's topics can be submitted through the question box. We will have dedicated time during the presentation to answer any questions from the audience. Finally, we really want to know what you think about our webinars and how we can keep improving. You will be sent a short survey after the webinar ends. Please let us know what you think, or if you have any comments or suggestions about the webinar. Next slide, please. A little bit about Eco Canada. Eco Canada's vision is to build the world's leading environmental workforce. Eco Canada seeks to help environmental workers succeed at each step of their career journey. To do this, Eco Canada has developed programs tailored to individuals at different stages of their careers. Eco Canada also provides opportunities for new workers to break into the environmental sector through wage funding for co-op students and recent postgraduates. For those already employed as environmental workers, Eco Canada provides the Environmental Professional EP and the Environmental Professional in Training EPT certifications, as well as the EPT student. Lastly, Eco Canada provides opportunities for those with vast experience as environmental workers to provide guidance and direction to Eco Canada's products and programs through advisory committees and memberships. Now I will pass it along to our speakers, Pat and Stefan, to teach you all about housing codes.
Okay, great. Welcome everyone. I'm Matthew, or Matt, and
I'm Stefan.
Stefan over the other box. Just introduce ourselves quickly, and then we'll get started. So I'm a professional engineer. I live in Regina, and I'm a principal with Airtight Engineering. So we're a small consulting firm. We focus on building energy efficiency and mechanical design. We also do lots of building science training as well. So that's what we're here with you today to talk about. I'm also an instructor with Passive House Canada. So if you're familiar with the concept of Passive House, it's a high performance building standard focused on comfort and energy efficiency. And that's me.
I'm Stefan. I've been practicing mechanical design with buildings and houses for a number of years now. I also teach through Passive House Canada, and we at Airtight Engineering, we spend a lot of time instructing, but I focus professionally on residential energy modeling, mechanical design, and building science.
Okay, now we'd love to get to know you just a teeny tiny bit. So Layla, would you be able to do those 2 polls that we had?
Yeah.
Awesome. So we have 2 quick polls just to see roughly who's in the room, which is always challenging because there's, I think, over 100 of you registered. So
I'm just gonna start with this one.
So you guys get to make up your own definition of whether you're in Eastern, Western, or Northern Canada. We left that very open-ended, but just to see. Okay, awesome. So more in Western than Eastern, but a good mix across the country.
Should I move on to the next poll?
Yeah, 80%, perfect. Great. Great, and one more quick poll question for you guys.
Doesn't seem to be sharing this one, sorry guys.
Okay, that's fine. We could always get people to put in the chat while we're starting. Feel free to, if you want, you're welcome to put in the chat what your interest in taking this webinar was. If you're, the thing that we're looking for is are most of the people in the room residents who are interested because of their own home, or are you guys people who work in housing, in a housing group, and want to learn more from that perspective? Or maybe you're interested because you're a professional in another area but find this topic interesting. So feel free to put that in the chat if you like, and we can just take a little skim as we're going through and see who all is in the room. And while you're doing that, we will get started. So our outline today, I'm going to present our first half. We're going to talk for maybe 40 minutes, 45 minutes-ish, and then give 10 minutes for questions at the end. I'm going to talk about ventilation to start, and then Stefan is going to talk about airtightness for the second half. So I'll start with why ventilation in a home matters, why we care about it. We'll talk a little bit about building code. We only have a couple slides where we're specifically calling out building code, but know that all of our other content is really relying on the standards that building code give us as well. So we try not to keep it too kind of technical or code heavy, but that's always in the background of the concepts that we're talking about. We're going to look at where airtightness in a building can go wrong and how we can do it better as well. And then ventilation, where it can go wrong, how we can do it better. That's similar for airtightness. So we're going to talk about why it matters. We'll look at an airtight layer, different ways for finding leakage if you're looking to see how airtight a house is, and then reference to building code to how it talks about airtightness. So that is our agenda for today. We're splitting we're talking about two things, ventilation and also airtightness, and we're going to sort of talk about one then the other, but we want you to remember the whole time that that these two topics are really connected. And we like to think of a building as a system. So that means the building is acting as a whole. So if I change one thing in the building, it's going to impact something else. So we can't make a building more airtight without adding ventilation because the people in the building need to breathe. So we need to make sure that we're considering both of those things together. So even though we talk about them one and then the other, just recognize that they are intimately connected. Okay, let's start with ventilation. So sometimes there's a misconception in the building industry that buildings need to breathe. And the truth is a building does not need to breathe, but the people inside the building do. So often we confuse airtightness and ventilation in the building industry. So we think, oh, it's getting too moist inside my building. I need a building that breathes. Well, no, that's not true. We actually need a building that's well ventilated so that we're dealing with that moisture inside. So that's something that we sometimes hear as the building needs to breathe. And the answer is no, it does not. In fact, there was a building science textbook that was written by a gentleman in the States, Allison Bales. It came out a couple of years ago, and that was the title of his textbook was A Building Does Not Need to Breathe. Or I think it was A Building Needs to Breathe, ? Or does it? And the answer is no. So let's talk about ventilation and why we should care. First of all, This might be pretty obvious, but fresh air is important for our health, and it's very important for a healthy home that we've got good quality ventilation because we all need to breathe. So there are many pollutants or contaminants or things that we want to deal with inside our house to make sure that we're maintaining fresh air. So our ventilation system has two roles. The first is it's bringing in fresh air from outside, which is replenishing the oxygen we need to breathe. And then the second thing it's doing is it's removing any of the things that we don't want to be breathing in. So one thing would be CO2, that's what we exhale, and humans are okay with CO2 and various concentrations, but the more CO2 we have in the air, the less happy our bodies become. And if we get too much, we start to feel sleepy and we aren't thinking quite as clearly. Particulate is something else. So if you cook, if you light a candle, any of those types of activities where we could create some smoke, that is going to be particulate matter that is very damaging to our lungs if we have a lot of it in the air that doesn't get dealt with. So let's say you're frying some bacon and you've got some smoke coming off of that bacon. Well, that's impacting your health. VOCs, so that stands for volatile organic compounds, and we have lots of these in our modern homes. If you buy a new electronic device, say you bought a new computer or TV, or maybe you bought a new plastic toy, lots of times those electronic components, plastics, etc., are off-gassing into our space. Or maybe you put on some perfume, or maybe you've got a scented candle. Those also, any of those things that kind of make our nose crinkle a little bit, those are volatile organics, and if they stay in our air, they also impact our health. Something else that's important, this isn't in itself always a huge health concern, but it is a comfort concern, and that's moisture. So if we have too much moisture in our air, we create lots of moisture by all of our activities as people. That is also going to make us less comfortable, and then it may create mold, which will then impact our health. And then finally, radon. So depending on where you are in Canada, radon can be a bigger or smaller issue. And radon is a gas that is radioactive and it seeps from deep underground. So if you've got a basement or a crawl space and there's a crack or it's not very airtight, you get some radon into your house. We want to make sure that we're ventilating to help move any of that radon gas out of our house. So those are just some of the things that we want to keep out of our air and the reason that we want good ventilation. So here's an example. This is an example from northern Saskatchewan, a house with some moisture issues, and you can see some mold growing there in the surface of the stippled ceiling. So we create a lot of moisture as residents of our houses, showers, breathing, cooking, laundry. In fact, a family of 4, you can very easily create like two gallon milk jugs worth of moisture a day just from living your life. And so ventilation is what helps us move some of that moisture out of the house and keep our air a good moisture level. So building code can help us. The national codes in Canada can help us with understanding how much ventilation is appropriate for our house. So the building code has minimum ventilation levels that it recommends, and these are based on the amount of bedrooms in our house. So I just took the table out here. You can see as your number of bedrooms increases, you have to understand what exactly this metric is, but our minimum ventilation rate also increases. So we're saying the number of bedrooms is kind of a good approximation for how many people will be living in a house. Now, if you have a lot more people living in that house than the number of bedrooms, then that's a spot where you might want to put in more ventilation than the code recommends. And this is where we should recognize too that the code is the minimum. Sometimes we take the building code as like the best we can do, but really it's a good minimum bar, and we can often continue to improve above that building code too. Some other ventilation requirements in the code talks about extra exhaust for cooking. So I mentioned bacon grease or other, if you're creating smoke or grease while you're cooking, we want to make sure we're exhausting that out of our air. And then bathrooms. Obviously, we all like a bathroom fan or some sort of exhaust in our bathroom to exhaust smells. And the code also has many other design requirements. So one example would be, well, how far away should an exhaust be from a window that can open? We don't want to maybe exhaust air out of the house and then have that air get pulled right back into the window. So how far away should those two things be? Those are some of the other design guides that the building code would address. One of the challenges with ventilation is that heating up fresh air takes a lot of energy, especially in the winter when it's cold outside. So here's a picture of this, actually my kitchen window. It's not particularly airtight and it's pretty cold. And you can see that it's really cold outside. I don't know, this was like -30 day or something like that. So I wouldn't want to just open up this window at -30 to get fresh air in. So we sort of intuitively know that it takes a lot of energy to heat up ventilation air. So what can we do about this? And turns out that there is another way. So here's my question. What if there's another way? So let's say we've got a house and our ventilation is with a bathroom fan. So we're just exhausting all of that nice hot air out of our house with our bathroom fan. And what that's doing is it's pulling in cooler air from outside through all of the gaps and cracks that I have in my house. And that's how I'm getting my ventilation. But it's not very effective because I'm losing all of the heat off of that air leaving the house. And then I'm pulling in this cold air. What if I could somehow use the heat from that exhaust to heat up that fresh air that's coming in a little bit? And it turns out that we can. So that's where this unit called a heat recovery ventilator comes in. Often we'll call them a fresh air box too, because it's a little more obvious what it's doing. But here's a picture of a heat recovery ventilator. We don't usually locate them in the attic like it's showing here, but this is a good representation of what it looks like here. Let me just see, do I have a pointer or something? Oh, laser pointer, great. Oh, okay. What do I have to do for a laser pointer? Nope. Can't see the laser pointer. Anyway, it doesn't matter. Stefan, can you see my pointer zooming around the slide? Yeah, I'm seeing that. Okay, great. Well, you'll have my little finger pointing on the slides here. Okay, so what's happening here is this box is going to bring in some fresh air from outside. It's going to go through a little heat exchanger, so it's going to exchange heat, and then it's going to get supplied into the living space. And then I've got stale air that's getting pulled out of my kitchen, out of my bathroom, going to go through that same heat exchanger and get exhausted. So this little square in the middle, these air streams are not touching each other, but they're transferring heat. So my nice warm stale air is transferring some heat to my fresh air. These units can do a few things that are awesome. First of all, they provide continuous fresh air. So all the time we're getting fresh air coming in, as opposed to only fresh air happening when I take a shower and remember to turn the fan on. Second of all, they can recover a large amount of heat. So, not great one can recover 50% of the heat, so half of the heat that I would lose in that air, and a really good one can recover up to about 90% or a little bit more. Also, we have the opportunity to filter that air, so that's helpful, especially if we've got, say, wildfires that are creating lots of smoke. This unit, we can put some filters in and make sure we're filtering out some of that smoke. We can distribute that air better throughout the house, and it's just got 2 little fans, so it uses very little energy to run this unit. So here's my beautiful stars showing how beautiful this heat recovery ventilator is. So this is an actual heat recovery ventilator. This one is very dirty. You can see on the intake side, it's pretty dirty, but just to show you how it works. So outside we have that cold, fresh air. Inside we have that warm, stale air, and then we have 2 fans that are pulling the air in different directions. It's getting pulled in, and then they're crossing each other through this core, and the heat is getting transferred, and then those air streams are going their separate ways, and now our fresh air is warm and our stale air is cold. So how can they transfer heat without touching? Here's a picture of the core up close. So we would have one airstream, it's kind of like corrugated cardboard. So you'd have one airstream that's going through one set of holes, the other airstream that's going through these other channels, going the other direction. So they're never touching, but they've got little thin layers of plastic between them, and they can transfer their heat. We've also got units called an ERV, so an energy recovery ventilator, that can transfer both heat and moisture. So that can be helpful if you're in a really cold, dry region and you want to maintain some humidity inside. If you go with an energy recovery ventilator, it's going to help you maintain some moisture. So how is it that we have gotten away with not using something like an HRV up until now? Let's look at that a little bit. So here's a brief timeline, an evolution, if you will, of ventilation in homes in Canada. So back in the day, this is what home ventilation looked like. So we've got a house and it's pretty leaky. There's lots of gaps and cracks. Nothing is sealed very well. So when the wind blows, that's going to bring fresh air in. That's also going to push stale air out on the other side of the house as the wind blows. The other thing is we've got big wood stoves or fireplaces, and whenever you light a fire in that fire is going to draw a lot of air up the chimney and exhaust it out of the house, which in turn is going to bring in fresh air. So your wood stove or your fireplace acted as a ventilation unit in some ways, as did the wind. So we've got air moving through gaps and cracks, and then wood stoves also moving air through the house. Maybe sort of a more typical modern home might look like this. So it's still somewhat leaky, and so the wind is still pushing air into the house. Now we've got a bathroom fan that's exhausting some air out of the house, and that's drawing some fresh air in to replace the air that's leaving. And then we still have appliances, such as maybe you've got a propane or heating oil furnace or a natural gas furnace or water heater, and those appliances are still also moving some air. So now a modern energy efficient home, one of the big changes is we've made this house more airtight, which Stefan will talk about when he talks about how to do that. But we've made this house a lot more airtight. And maybe our appliances, we might have an electric heating system. Maybe it's a heat pump that's heating. We don't have any combustion that's moving air in or out of the house. Or maybe it's a high efficiency furnace that's sealed combustion. So it's got two pipes going in and out. It's taking air from outside. It's using that for combustion. It's pushing that air back outside. So it's not using any air from the house. And so now we need this heat recovery ventilator. So here's my picture of a heat recovery ventilator. So because there's nothing else really that's moving air in and out of the house, now we need something like a heat recovery ventilator to help make sure we have enough ventilation. So that's why on an old 100-year-old house, it's fine. You don't have any moisture problems. But on a new house, if you tried to get away without any ventilation, you would have moisture problems. Now, that's not to say that those old houses are healthy. So here is an example. This is one of our colleagues in Regina. So he did some tests on his own house. He's got a 1970s house in Regina. And what he found was that he's got pretty high particulate matter. So that's stuff like smoke from cooking, etc. So here is showing his particulate matter concentrations. And then he's also got a radon detector, and his radon is quite high. This is much higher than we would recommend for radon levels. And he doesn't have a full house ventilation system. He just has a bathroom exhaust fan and a kitchen exhaust fan. And the kitchen exhaust fan wasn't working. So really he just has bathroom exhaust. So not enough ventilation for this particular house means he's got poor indoor air quality. And even if he can't tell in a particular day, over time, that's going to impact his health. Here's another example of it going wrong. So here is a house in Saskatchewan as well. And they do have an HRV. This is a new house. It's maybe only 5 years old. It's very airtight. They do have an HRV. However, they were finding it was too dry in their house when they ran their HRV all the time. They wanted more humidity, and so they turned off their HRV and they only ran it after they had a shower. And it turns out that was a really bad idea because you can see that they've got some black mold happening. They've got a ton of condensation. They've got damage to their window casings on the outside. So a lot of moisture issues because they weren't ventilating properly. So The windows also were not the best quality, and so that wasn't helping. That was probably also a contributing factor, but one of the contributing factors was likely not enough ventilation. Okay, so let's talk briefly about how you'd install an HRV. I won't go through this in super detail, but just this is what an HRV installed might look like. It's got 4 ducts. 2 are going to the outside, and we're going to make sure those ones are insulated. And then there's 2 going to the inside. That's warm air in there now, so we don't need to insulate those ducts. We've got filters. So this unit has the filters. You can see right on the front, so we need to make sure we can change those easily. And it's got a drain underneath. So there's a little trap and a drain for condensation. So if there's any condensation that gets collected in here, we want that to be able to drain out. Something else is these insulated ducts, we want those to be as short as possible. So we don't want to have those insulated ducts running all the way across the house, because then we're actually losing a lot of heat through those ducts just because they're so long. Here's an installation that is not a good idea. We've seen this lots in northern communities, but this is generally a bad idea, and that's putting an HRV ventilation unit in the crawl space. Because we have filters in this that need to be cleaned, and the unit should be checked and cleaned every kind of 3 or 4 months, similar to a furnace, it's really tough for a resident to remember to do that if it's in the crawl space. And if someone has some mobility challenges, then they're never going to do that if it's in the crawl space. So we have seen, I don't know if I've ever seen an HRV in a crawl space that actually has been maintained. So we would recommend not putting one in a crawl space. Here's what a more typical installation in a mechanical room might look like. This one is using flex duct. Flex duct is used very often. It's because it's easy and it's cheap. It's not the best just because it can really, it can kink very easily. And then you think you're getting lots of airflow, but you actually aren't. So when we see pretty tight bends, there's potential for kinking underneath this insulation. So even though it gets used all the time, you have to make sure it's installed well and stretched out. If it looks kinked, it probably is. And then here's there's just a little pigtail trap on the bottom. So here's where that condensate, so any moisture inside the unit can drain out. And a picture of that little pigtail trap. So this one isn't quite as robust because it can dry out, but this is pretty common. You see this often. Something else to note is we want to make sure we don't have an extract for our HRV that's super close to our stove. We would want maybe a range hood over top of the stove that exhausts outside instead. Here's an example why. So this is our coworker's fan. There's a small bathroom exhaust fan that was installed right over top of his stove, and you can see all of the grease that's collected in here and collected on the fan. So we don't want anything like that making it back into our HRV because that's going to be really hard to clean out. Something else that's really important with ventilation systems, and this often gets missed in Canada in residential construction, and that is commissioning. So an HRV is designed to pull in a certain amount of air and push out the same amount of stale air. So if we're pulling in 100 CFM of fresh air, we want to make sure we're pushing out 100 CFM of stale air. And sometimes what happens is a ventilation unit will get put in and there will be no balancing of the sides of it. And so who knows, maybe it's pulling in 50 CFM and pushing out 100 CFM. And so we want to make sure that it's balanced, and that's called commissioning. So that's making sure that the unit is balanced and is bringing in as much as it's pushing out. We also want to make sure that it's matching the actual ventilation rate that the building code requires. So if the building code said 50 CFM is the requirement, and the unit we put in, let's say we have ducts that are kinked and are not flowing well, and it's only putting out 40 CFM, we want to make sure that we can unkink those ducts and increase the flow so that it's matching what we designed. Here's a picture of me, a couple of pictures of me commissioning a system close to Regina, maybe 45 minutes away. And the last thing that's super important for a ventilation system is cleaning. So here is here are a number of pictures of aspects of a ventilation system that have not been cleaned or maintained. And if this is our fresh air box, you can imagine that it's really not helping provide fresh air at this point, because we've got a lot of dirt, a lot of debris, and plugged diffusers, plugged intakes, and so it's going to be really hard for this unit to do its job and provide good quality ventilation. So with that, I'm going to hand it over to Stefan to talk about airtightness.
Okay. So now we have a functioning ventilation system in our proposed house or building. And it's important that we start with that first. We don't want to start with airtightness and suffocate the residents. So we have our ventilation system in place, whether that's exhaust fans or an HRV or some combination of those. Now we want to focus on making our house airtight. So how do we exactly do that? So start by sealing up the leaks, basically. And I'm sure everyone has experienced a cold draft in the middle of winter, either by that door that looks like this, where the door sweep is worn out or broken, needs replacing, or by a window with a cold draft. And no one enjoys that. It's not only uncomfortable, but it will use a ton of energy, because this cold air is leaking in. Now our heating system has to make up for that. At the same time, hot air is leaking out, and that's just wasted to the outside. So it's uncomfortable, use a lot of energy, and we can also have a lot of moisture movement with the air going in and out of the house where we don't want it to. And that can cause some issues with rotting things out. And the other consideration here is that if we have an exhaust-based ventilation system, that means our fresh air is going to be coming in through gaps and cracks like this seen here, and that's going to be unfiltered. So we could be bringing in pollutants, dust, pollen, insects, all kinds of things that we don't want in the house. So it's always best to have some sort of filter system on the intake air. So now using an example that hopefully everyone is familiar with, a nice wool sweater like this, it's going to be nice and warm if you're inside, or some sort of shelter away from wind, or if there's no wind outside. It'll be nice and warm. But as soon as there's any amount of wind, it's going to blow right through that, and you're not going to feel too warm anymore. So this, in combination with like a wind jacket or a shell, that's going to be nice and warm even on a windy day, because we have different layers, one stopping the wind and one stopping the heat. So in the same way, our house, it's going to leak air wherever air can leak in and out. So this is typically around penetrations in the building envelope. So doors, windows, every time a pipe comes in, wires going in and out. We have various appliances with fans, ducts, chimney. All of these areas are potential areas of air leakage. So a few ways that air can move through a house, just kind of either passively or actively. So if it's a windy day, we're going to have air coming in the one side and exiting the house on the lee side. One thing that we see in tall buildings especially, it's called the stack effect, where warm air rises and that escapes out the ceiling, and upper story walls and wherever it can escape. And then that same amount of outdoor air is going to sneak in lower down in the building, wherever it can find an entry point. We can see a reverse stack effect. If it's hot outside and we're air conditioning on the inside, that can be reversed. And then lastly, at that fourth image, now we have combustion appliances, exhaust fans, various devices that are either pulling or blowing air into or out of the house. So all of these things are potentially happening at the same time. So we just want to stop that and be able to control exactly how much air in and out of the house that we actually require. So here's an example of the stack effect. And here we are, this image is from a upper floor of a building. And we can see just naturally that stack effect taking place and air wanting to escape out the ceiling there. So it's creating a pressure difference from the upper to the lower floors, and then air is going to move accordingly. Now, I also mentioned that we have vapor movement with air movement through our walls and our building assemblies. That air is going to carry moisture with it. So we can have this moisture diffuse through our walls. And one way we do that is, prevent that is by having a vapor barrier to stop it on the warm side of the wall. So all that moisture that we create doesn't just end up in the wall. But if we have an air leakage, a hole in that air barrier, then even a small leak can carry a ton of moisture in all of that air. So actually, when we're talking about vapor movement and controlling it, airtightness is paramount. That's very important for controlling vapor movement, is an airtight building envelope. And so that air leak can carry 10 or 100 times the amount of moisture as what we would see through diffusion through a much larger area. Airtightness always being very important. So here we can see an example. We have frost on the underside of the roof deck, and your first reaction to this might be, oh, there must be a leak in the roof shingles, but actually this is caused from an air leak in the ceiling. So what we have happening is we're producing warm, humid air in the house. It sneaks out through a little hole in the air and vapor barrier on the ceiling, makes its way into the attic, and at some point it touches the cold underside of the roof deck or the screws or nails poking out, and condenses on that cold surface. And if it's really cold, then it'll freeze, and all winter this is just going to build up more and more and cause all kind of problems because it wasn't airtight. So how do we find and stop air leakage? So first we have to identify the air barrier. What is the airtight layer? So typically in residential construction, it is a 6 mil poly air and vapor barrier on the interior. And then this is transferred to the windows. We're going to seal this poly vapor barrier to our window frames and kind of create this balloon around the entire house. Now, we can also use taped plywood on the example on the right. We can also use an exterior air barrier, as shown on the bottom photo there. And the thing to keep in mind is it needs to be continuous for it to be effective. Because if we create a nice air barrier over most of it, the air is going to find that leak that we didn't seal it up and travel through there. So in the same way that we need to think about a balloon, if we have 90% balloon, it's not going to work. We need 100% balloon for it to actually function. So same is true for a building envelope. We want that continuous airtight layer all the way around the house. So one way we help a lot of builders and designers do this is to look at a section of the building, kind of a cut right through the building, and identify the airtight layer all the way around the house. So we want to have a continuous line and make sure we know what material we're using, how we're going to seal it to the next material, how we're going to get around the floor and transfer around windows and make it continuous. And so, like I said before, most of the time it's a 6 mil poly on the interior of the house. And this poly layer is functioning as the air barrier and the vapor barrier in this case. But then we go in and get the electrician and the plumber to install their things, and they poke a whole pile of holes right through our airtight layer. So then we have to go in with poly pans, sealant, tape to seal up those penetrations. And this can get difficult and complicated depending on the project. A much better approach that we've been advocating for is to have a service cavity. So this would be separating your interior finish from your airtight layer, so that the plumber and the electrician can run all of their wires and pipes without having to go through that airtight layer. This is quite nice for the trades because they don't have to be going in and out. They can just run it all inside. It can be a quicker install in those cases. The other advantage too is after occupancy, every time the occupant hangs a photo or a coat hook, they're not punching a hole through that airtight layer. So the building is going to remain airtight over time. I said before, we can have an exterior air barrier. So here, the light blue membrane, it is airtight, but it is vapor open. So we're using it to stop the wind and the air movement through it, but we're making sure we're not trapping moisture. And in this project in particular, there's two air barriers on the walls, just in case one gets poked, then we still have a nice continuous air barrier, and the building's going to remain airtight. So we can use multiple air barriers. Something to note here is that all the little squares of tape, those are taping over staples and other little penetrations that were made in the membrane. Some examples of poor air barrier installation. We see here in a crawl space, not all the poly was sealed to each other. It wasn't sealed around penetrations. There aren't good covers, and we can see the poly was dirty or wet, and so the tape is not sticking very well. And here we can see an improvement. A little cleaner, a little more continuous. And moving on to windows. Windows can be a very big problem area if they're not done properly. So here's a really good example of having that airtight layer on the exterior is taped, and it's taped properly so that if there is any water, it's going to be able to drain away. And then on the interior, we see that the airtight layer is taped to the warm side of the window frame. So now we have nice continuous air barrier, and we're also protected from any liquid water on the outside. Moving on here, sorry, there's a bit of a lag when I advance the slides, but so moving on, how do we find the air leaks? So we use a blower door to depressurize the house, and then we walk around the house with a smoke pencil or a thermal camera, and we can find and see all the leaks and seal them up really quick. So schematically, this is how it works. Our blower door is a big fan in the front door, and it's blowing out, depressurizing the house, causing outdoor air to sneak in through all the gaps and cracks, and then we can see that, we can feel that with the back of the hand, or see that with a thermal camera here, or a smoke pencil, and then fairly quickly tape up that hole and make the house nice and airtight. And so this is most effectively done before there's drywall on, while you can still get at the airtight layer. And so the infrared camera, or thermography, is just showing a hot dog, but also to notice in this photo is we can see the cold from the air leakage around the bottom of the door. So these thermal cameras allow us to see hot spots, which are the whiter, the hotter, and cold spots, the darker, the colder. So we can pretty quickly see any cold spots or air leakage. So common area here we're in the basement, so around the rim joist, the floor system. Typical big area of air leakage, and we can see that quite clearly there. Another thing, this would be just upstairs, and we can see some of that cold blue air coming in underneath the baseboard, underneath the wall, because there's an air leakage around that entire floor system. Here's another example. This project, they have a nice membrane that's taped, but then they didn't quite seal it to the floor or around the floor. And we can see a nice big air leak there. So it has to be continuous. Here we have an attic hatch that does not have a good gasket or seal around it, so we can see lots of cold air coming in through there. Another common area are outlets on exterior walls. So with the blower door and the thermal camera, we can see a whole pile of cold air coming in through that, because the electrician made a hole through that airtight layer, and now we've got cold air potentially coming in. A light fixture on a ceiling, same thing. We have an electrical penetration through our airtight layer, and the thermal camera makes that very obvious. Here we have an example of the floor system in being a typical problem area. And especially in a case like this, where they're using multiple different products and layers and trying to make that airtight. But here we see if the builders were to ask themselves the question, what is the airtight layer? In this case, downstairs, it starts with poly, then there's acoustical sealant, then it goes to the top plate, then there's spray foam, then it goes to OSB, then there's acoustical sealant upstairs, and then poly again. So 6 connections. Now, are any of those 6 going to fail over time if there's any type of movement in the building? So we just want to keep it simple. We don't want to have all these different connections. So in the building code, there are some, it does reference airtightness and specifies some different values that are required for new buildings. And it requires that the air barrier be continuous. There's also some guidance and some examples of construction details. So to summarize, good airtightness and ventilation are very important for creating a healthy, comfortable, and energy efficient home. So we first need to provide good mechanical ventilation, and then we can make a house airtight. And after both of those, then we can get nice and comfortable and energy efficient. And heat recovery ventilators are often the best option for providing good ventilation and being energy efficient at the same time. And that is all we had today. So if there are any questions, feel welcome to in the chat or ask directly.
Thank you, Stefan and Matt. So as Stefan was saying, if you have any questions, you can submit those to the question box, and I'll just read those aloud for our presenters here. So our first question is, how can I apply this logic to my 120-year-old home, which has 0 moisture barrier anywhere, keeping in mind that I have no interest in the expense or effort to remove all of my brick siding and excavate my foundation to completely moisture wrap it from the outside?
Yeah, that's a great question. So you certainly will be more limited. Maybe, yeah, I'll give my thoughts then, Steph, if you have any. With an old building like that doesn't have a good air barrier. Usually in those old houses, the thing that was the airtight layer is the drywall or the plaster. And so probably your best bet is to try to make that drywall or plaster layer as airtight as you can again. So that might include patching cracks. That may include, maybe you take off baseboards and you seal the plaster to the floor or the subfloor behind your baseboards and put it back on, or you could even just caulk around your baseboards. And then really looking for what are the large gaps and cracks that you can address. So maybe it's weather stripping around your doors. Maybe it's some of your penetrations in your basement. Those are all spots that you could look for. And as well, are there any areas where there's not a finished surface? So maybe there's maybe you've got a portion of crawl space or basement that's not a finished space that it's easier to make a change to without ruining a bunch of the finishes in your house. So that's what I'd recommend. I don't know, Stefan, anything to add?
Yeah, I would say ventilation system first, and then airtightness. So whatever ventilation system you have, I'm going to assume you have an exhaust fan in bathrooms and kitchen. So having them in working order is probably the easiest. If you want to upgrade your ventilation system, you could install HRV system, and that can be done various ways. But once you have good fresh air, good ventilation, then you can go around and find all the leaks and seal them up as best as you can.
Perfect. That was very helpful, guys. We got a heart from our questioner. So the next question is the heat recovery ventilator usually installed in the attic?
No.
The answer is no.
No, it should be.
Yeah.
Sorry.
Go ahead.
Go ahead. Okay. It should be installed in the mechanical room, usually by, like right beside your other equipment, furnace, air handler, laundry, something like that. In a room that you can get at and check and change the filters easily and regularly.
Perfect. Our next question is, how do you easily detect air leakage that's not visible in a house or apartment without investing in high costs?
I would say the easiest way, cheapest way is to turn on all of the exhaust fans. So this would be bathroom, kitchen, maybe even clothes dryer if there's a vent to the outside. And then go around with the back of your hand and try to feel any cold spots, cold drafts. That would probably be the cheapest and easiest way. It would cost nothing, and just take a bit of time to find the cold spots. This is obviously a little bit easier with a thermal camera and a blower door, because the blower door is just a huge exhaust fan. So we can make sure that we're going to find all those leaks, turn them into big leaks. And that could be pretty affordable. We can do a lot with a blower door and thermal camera in a couple hours. So that might only be a few $100 to hire someone to do that work. And yeah, maybe, Matt, if you have any other thoughts on that.
Yeah, the only things, I think that's great. The only things I would add would be if you're checking for leaks, it's going to be easier to feel them on a cold day outside because that air coming in will be colder. Another thought is if you're hiring someone to do a leak test, you don't need a full like EnerGuide audit. You could hire an auditor just to come and run a blower door, so that'll be a little cheaper. And then my final thought on that is one thing you can do is just look for all of the spots that are common culprits. We showed a slide of that, but if you look on the website, in the Enercan Keeping the Heat In website, they show all the locations that are common culprits. So sometimes you can just look there for gaps and cracks. You might not even need to feel cold air to say, maybe I'm going to put some tape here or run some caulk in here. So that could be another option too.
Perfect. We got a few more questions. We'll see if we can squish them in. So with HRV units, what are your thoughts on HRV preheaters?
Yeah, great question. So two thoughts. So a preheater is to help address frost in the HRV. So as it gets colder outside, often you'll get some frost buildup in the HRV. And so different HRVs have different ways of dealing with that. So one way is the unit will go into a defrost mode where it'll just exhaust air for a little bit and warm up the unit, and then it'll go back into supplying and exhausting. Or it might recirculate air, and then one way is to provide a preheater. So the benefits of a preheater are you get continuous fresh air. The unit is never going to go into a defrost mode and stop providing fresh air for you. The drawback is it's going to be higher energy cost if electricity is expensive where you're located, because often we're just using an electric resistance heater in that duct. And so that's sort of the trade-off is you get better ventilation, more continuous, but you're going to pay more energy costs to keep that unit running all the time. So that's like simplification, but in a nutshell.
Perfect. So we are unfortunately out of time now. So thank you very much to both Stefan and Matt for your time today. We also have some more upcoming webinars and events, so be sure to check out our event calendar to see if there's anything that interests you. And thank you everyone for coming today, and enjoy the rest of your day.
Awesome. Thanks, everyone.